So today's material is isomerism. Oops, starting on the wrong slide. Isomerism. That's what we're talking about today. Now this may be kind of tough because you're going to have to kind of stretch your brain a little bit. So we're going to go over it today, do lots of examples, and then on Wednesday I've got enrichment for you to do that will really, I think, kind of seal this up. So isomerism is the topic for today, isomers. Let's talk about rotating around a bond. So when you've got a carbon-carbon single bond, okay, carbon-carbon single bond, this bond freely rotates, okay, free rotation, meaning this can rotate, fully, okay? And if this is rotated like, say, that, is that a new molecule or is it the same thing? It's the same thing, right? If I stand on one foot, am I a new person? No, I'm just stand on one foot, right? This rotates freely, okay? So that free rotation makes things that are called conformations. In other words, one is more stable than the other. Just like I can ask you, is it more stable to stand on 2 feet? Or more stable to stand on 1 foot, or more stable to stand on your head, right? You're still the same person, you're just oriented slightly differently. That's called conformations. These are not new molecules. You haven't created a new molecule by rotating this bond, right? Now, when we get to double bonds, there's not free rotation. That's something that we'll see in a double bond that is locked in place. Single bonds, however, have full rotation, and you can give different arrangements, okay, because this can rotate. And so it's called a conformation. And there are versions that are more stable than others, just like it's more stable for me to stand on both feet, especially with big belly, than it is to stand on 1 foot or do a handstand, right? The staggered is more stable because it puts them further apart, and the eclipsed is less stable, okay? Let's talk about what staggered and eclipsed look like. So I'll try to put it so that the screen can kind of make a shadow here. So this would be eclipsed, right? Can you see how this is directly behind the other? They line up with each other. They're right on top of each other. This is called eclipsed, okay? Why is this less stable? Because these are just hydrogen atoms. But let's pretend that this is something, a big atom, a big bulky atom. Now they're smashing in each other's face, right? That would be less stable. Whereas if I rotate this, can you see down the line? Now I've got 2 up and 1 down, 2 down and 1 up, right? That one's called staggered. Now everybody's got more breathing room. That's more stable, okay? You can think about it in a lot of different analogous ways. Is it more stable to stand in a crowded space or a space where everybody's got room, right? It's the same idea. So let's, instead of having a hydrogen atom there, let's substitute something a little bulkier. Some atoms on it. By the way, a model kit is really helpful. It's not a required course material for elementary organic, but you will definitely want to buy it when you take Organic 1. Some model kits are better than others. I can give you my personal recommendation. All right, so now we've got bulky groups, and it makes a big difference now, right? Here would be, which one is this? I won't tell you. You tell me which one this is. This one is what?
4 carbons.
Right, we're looking straight down this bond right here. We're looking straight down this bond. And we're looking at the orientation of these two to each other. This will be eclipsed, right? Because these two are crashing into each other. That would not be more stable, right? If we rotate this, there's staggered, right? But is this molecule different in terms of its name? No, it's still the same molecule, right? This bond is just rotating here, okay? Staggered versus eclipsed. Eclipsed is a lot less stable, right? Especially once we start getting big things involved, right? These are going to be crashing in each other's space. They're not going to like it. It's not going to be stable. Whereas staggered, everybody's got some breathing room. That is more stable. And so here are some pictures. Right? This is the molecule that I just made. What is the name of this molecule? 1, 2, 3, 4. It's just butane, right? So when you're looking at down the bond here, right, what do you see? You're looking straight down the bond. You've got this CH3 up You've got this CH3 down, right? And then the rest are just hydrogens. So we're just looking straight down that line. So which one is that? Staggered or eclipsed? That one's staggered, right? And then there's eclipsed, right? This is behind this one. They're crashing into each other. But again, is this named any differently? No. Conformations are just the result of rotating along a carbon-carbon single bond. So if I had a mixture of these in a lab, let's say I had, and you couldn't, the answer is you couldn't, right? But let's just pretend, could I isolate just these from each other? If I had a mixture of staggered and eclipsed, could I get all the staggereds in one beaker and all the eclipsed in another beaker? That wouldn't be possible, right? That's free rotation. Right? So there's free rotation. Staggered is more favored. We'll be talking about this a lot, which is what I just said. There's no separation method that you could use to separate this from this because they're freely rotating, okay? That's important because when we talk about the next kind of, when we talk about isomers, isomers are not the same thing as conformations, okay? Conformations are me standing on one foot versus me doing handstand, right? I couldn't separate myself from that. That doesn't make sense. Isomers, on the other hand, you can separate isomers. Okay, they can be separated in the lab. They're going to have different boiling points. They're going to have different names. They're going to have different melting points. They're going to have whole different physical properties. Okay, so conformations are the same molecule. You can't have a different boiling point from yourself. Now, isomers, like I just said, are two molecules that have the same formula but different structures. In other words, the atoms are put together differently. So the criteria to be isomers, they must have the same formula. They got to have the same formula, but they're going to have different names. Same formula, different name. Those are the criteria. And there are two types of isomers that we're going to look at, structural isomers and stereoisomers. We'll do structural isomers first. Isomers are not the same thing as conformations. Okay, butane in the staggered version versus butane in the eclipsed, they're both named butane, right? Same formula, same name, that would make them isomers. But same formula, different name, that would make them structural isomers. And just FYI, some textbooks call these constitutional isomer, depending on the textbook you're looking at. Structural isomers, some books call it constitutional isomers, it's the same thing. Okay, so let's go through some examples here. Structural isomers and stereoisomers are going to be different for each other. They're going to have different physical properties. So that means we could distill, right? We could boil the one with the lower boiling point off first. We could use chromatography. We could use a lot of different things. They're going to have different IMFs. If you have different IMFs, you'll have different physical properties. All right, that's what I just said. So let's look at some structural isomers of C4H10. All right, well, here's one of them. That's the linear. That's not the favorite conformation. There it is. Right, that's butane. That's one of them, C4H10. Right? But there's another one. If you took this methyl group and stuck it right there, would that still be C4H10? So in other words, we're going to do a swap. That'll work. So if we put this, right, this is not one of the kits I would recommend because I think that comes apart too easily. You put this right here and this right here, we just did a swap, right? Have I changed the number of carbons? Have I changed the number of hydrogens? Nope, it's still C4H10. Is this the same name? Looks like a Y, right? Does that have the name butane? No, it doesn't. What's the name of that? 1, 2, 3. So that would be methyl propane, right? And you could call it 2-methyl propane, but technically that 2 is not necessary, right? Why is the 2 not necessary? Because the only way you're going to have a methyl group substituent on a propane is if it's on carbon number 2. So that 2 technically isn't necessary. But notice, remember when we talked about intermolecular forces? Linear things versus branched things, they have different IMFs. They're both going to be nonpolar. They're both going to have London forces only, but the London forces are stronger in this one, right? And notice it's got a higher boiling point. They're both gases at room temperature, but that's a pretty significant difference in boiling point, -12 versus -0.5, right? This one's got stronger London forces. They stack on top of each other nice and neat. So those will be called structural isomers. Same formula, different name. So those are the criteria you always have to ask yourself. First, you got to count all your carbons, count all your hydrogens, make sure they have the same formula. Because what if they have different formulas? If they have different formulas, then they can't be isomers, right? They would just be unrelated. If one was C4H10 and one was C4H9, those are unrelated compounds, right? They have to have the same formula, different name to be structural isomers. Okay, so it takes a little bit of practicing, just kind of play around with it. So let's play with structural isomers of C5H12. Well, the easiest one's going to be the linear, right? Just straight up pentane. That's the easiest one. And just like I did a minute ago, right, what did I do to make this isomer? I swapped one of the methyl groups and a hydrogen, right, because this is what I had originally. And I said, okay, let's take this, put it over here, take this, put it over here, right? That's what I did to make that isomer. You're going to do the same thing here. So let's take this. Now, could I put it right here? Would that make a new thing? If I put this CH3 right here? No, because it'd just be the same molecule, right? It'd just be bent. So I need to put it at least 2 carbons down, right? So if I take one and put it over there, oh, I started on the other end, but you get the same idea, right? That gives me 2-methylbutane. Again, the 2's not really necessary, right? Because if a butane's going to have a methyl group, by definition, it's going to be on carbon 2, right? Because even if what if I took it and instead of putting it right here, I put it right here? Would that create a new creature? If I have this CH3 right here, imagine this CH3 right here. Is that something new? No, it's not. Good. Why? Because it's still 2-methylbutane or methylbutane. There's another isomer that we could make. What's another one we could do? Can you see it? What if I yanked this off and put it right here and put this hydrogen right here, made a T? Would that be the same formula? It'd still be C5H12, right? But it would just be put together differently. And it would have a unique name, right? This would be 2,2-dimethylpropane. Now you would have to put the 2,2 there. Well, I mean, I guess technically you could, because but there would be 2 methyl groups on carbon number on a propane. But I still want to see it, just to make sure you know the rule. Do you see how we made this? Now, there are only 3 structural isomers for C5H12. But as we increase the length of the chain, the number of isomers goes up significantly. So this is what I said a second ago. Instead of putting this right here, what if I put it right here? Does that create something new? It doesn't, because what's the name of this? Right, it's still 2-methylbutane or methylbutane. Good. So see, I don't know if you can draw all of them, but see how many of them you can draw for C6H14. And also, as a self-check, give each one of them a name. It'll practice your nomenclature. If you see the same name appear more than once, you know you haven't created something new. So try this one. I'll pause the video. All right, let's see how many we came up with. There are 5. Straight up hexane, right, that's linear. Then we take one of these methyl groups, swing it over here, we get 2-methylpentane, which you would need the 2, right, because you could have a methyl group on a pentane on carbon 2 or carbon 3. That 2 is absolutely necessary, right, because you could have a methyl group on carbon 2 in a pentane or carbon 3 in a pentane, and these would have unique properties. You could also put both methyl groups on carbon 2, or you could have a 1 on 2 and 1 on 3. So those are your options. And they're all going to have unique properties. They're all going to have unique boiling points. They're all going to have unique melting points. You could separate a mixture of these in the lab. Did you get all 5?
No, I got 4.
Which one did you forget?
I did 3 methyl pentane, not 2.
Oh, okay, gotcha. Why don't you try another one? These are isomers of C7H16. See how many you can come up with. There are a lot. I'll give you that. All right, let's see how many you got. So straight up heptane, that's the easiest one. On a test, I would not let you pick heptane. I'd say other than linear, draw and name some structural isomers. Did you get 2-methyl and 3-methyl? Could you do 4-methyl? Why not? You'd just be starting from the other end, right? Did you get 3,3-dimethyl? You could put both of them on carbon 3, right? What about 2,4-dimethyl? Did you get that one? You could also do 2,3, 1 on 2, 1 on 3. You could do 3-ethyl, put an ethyl group on carbon 3. That would work. You could do 2,2,3-dimethyl, or you could do 2,2-dimethyl. Right? You could put them both on number 3. You could put them both on number 2. You could split them up between 2 and 4. You could have an ethyl group, or you could have 3 methyl groups. So, like I said, on a test, I would not say draw all of them. I would say, other than linear, draw and name 4. Right? That is fair game. Okay, that's what I just said. Let's see how many you could come up with for C8H18, just for fun. I wouldn't ask you to do that on test, just for fun. See how many you can get. All right, let's see how many we got for this one. Okay, there are 18 structural isomers, right? As you increase the length of the chain, you're going to get more and more and more and more and more structural isomers. So 18, you came up with 18. Woohoo, good job. Like I said, on a test, I would say draw and name 4 other than linear. Obviously, I wouldn't accept octane because that's linear. But anything beyond that, I would have been okay with. Do you see the ones you came up with on that list? Or ones you derived on this list? Okay. Okay, here's a problem for you to do. Look at these two molecules and decide, are they structural isomers? Are they the same molecule, just drawn differently? Or are they totally unrelated, no relationship whatsoever? So what are the criteria? To be structural isomers, they have to have same formula, different name, right? To be the same molecule, they would have the same formula and the same name, right? And to be unrelated, they would have different formulas altogether. So take a second and look at this. Decide which descriptor fits this family. Oh, I just gave the answer. Oh, well. Well, when I paused the recording, you saw the answer, which is kind of a bummer. But let's talk about why the answer is what it is. Okay, so what is the correct answer? They are the same molecule, right? They both have the same name. They're both 3-ethyl, 4-methylhexane. If they have the same formula and the same name, then by definition, they're the same molecule, right? Can't be different if you're the same. Kind of a duh statement. All right, here's another one. Structural isomer, same molecule, or unrelated. I'll pause the video and let's try this one. And this time you won't see the answer. So I planned ahead. Okay, so you always want to count your carbons. Make sure that they have the same formula, right? Because if they have different formulas, then we automatically pick which one. If they have different formulas, it would be unrelated, right? Because if one's a nonane and one's a decane, well, that may not mean that they're unrelated, but if one's got 15 carbons and one's got 14 carbons, that means they're definitely unrelated. So you can't go by name to determine if they're unrelated. You have to go by formulas. So these are structural isomers. They're both C11, H23Br, right? So if we're counting hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Right? So you count your hydrogens as well. But they have different names. Right? So these have the same formula, different name, that makes them structural isomers. Do we agree? All right, here's another one to try. Same molecule, structural isomers, or no relation. All right, let's go through this one and see what we got. So we know that there are two bromines. Woohoo! We just need to count carbons and count hydrogens, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So what do we get here? No relation, right? They can't be related. One's an 11 carbon chain, one's a 13 carbon chain. No relation, right? You can't go by the name, because by the name they're both octanes, and you're like, aha, they must be structural isomers. But when you count your carbons, one has 11, one has 13, no relation. Okay, so same formula, same name equals same molecule. Same formula, different name means structural isomer, same thing as a constitutional isomer. Different formulas, no relation. Can't be related if you don't have the same formula. In terms of structural isomers. Make sense? We good? Okay, now this is from your textbook. Kind of puts it into perspective, right? That would be the example of a conformation, right? Dog standing on one leg versus dog standing on four, which is what I said, you know, about standing on the two legs thing. Whereas here would be isomers. You're taking the tail and putting it in the place of the leg, right? It'd still be the same pieces, just connected differently. I'm not sure you'd classify that as a dog anymore. Okay, now we do have another kind of isomerism called cis-trans isomers. This occurs in molecules containing double bonds, which we'll talk about next week. And it occurs in rings, which will be our next lecture. So we're not going to do that today. Now let's talk about stereoisomers. These are molecules that are connected the same way, but oriented differently in three-dimensional space. You might think, well, how can they be connected the same and oriented differently? That sounds funny. Well, we're going to look at some examples. Same connection, different orientation in 3D space. And this is where a model kit is useful, especially if you're planning to take Organic 1. You spend a lot of time on stereoisomers. Model kits are really useful for that. Okay, so just think about you and your mirror image, right? If you go up to a mirror and you try to shake hands with yourself. Hi, self, nice to meet you. What happens when you raise your right hand? What's your mirror image doing? Is it your right hand or is it your left hand? It's your left hand, right? You reach your hand to shake, you can't shake hands with yourself, right? You're non-superimposable on your mirror image, in other words. They don't line up. Doggy looking at a picture of himself, mirror image of himself, right? It's the same way with molecules too. If you place them on top of their mirror images, it's not going to line up. Something's going to clash. It's not going to work. And so enantiomers, which is another word for stereoisomers, they mean the same thing. Molecules that are not superimposable on top of their mirror images. Enantiomers are the same thing as stereoisomers. They cannot be superimposed on top of their mirror images. You are enantiomeric. You cannot be superimposed on top of your mirror image. And this is something that we just kind of scratch the surface on in elementary organic, but in full Organic 1, you'll spend a long time doing stereochemistry. A lot of time in Organic 1 and Organic 2. Okay, so for instance, socks would not be enantiomeric, right? Because they're the same on both sides. Socks are not enantiomeric. But your hands would be, right? Take off your rings. If you have your hands, is there a plane of symmetry between them? Yeah, there's a symmetry. I mean, excluding things like, cuts and freckles and all that stuff, right? There's a mirror image here, but if I take my left hand, can I put it on top of my right hand? It doesn't work, right? Pinky goes where thumb is, thumb goes, it doesn't work. But like I said in the previous, a sock, right? A sock would not be an enantiomer. Your hands would be. Your feet, you can pick any part of it. Your whole self, you as a whole are enantiomeric. So when we do drawings in 3 dimensions, we use some notation to show kind of where things are oriented in space. So a wedge means something that's coming out of the screen. Okay, so this wedge means something's coming out of the screen. This dash means that it's behind the screen. And then anything that's in a straight line is inside the screen. Okay, so wedges mean they're coming out. Dashes means they're back behind the screen. And then the straight lines are things that are in the screen. And again, we go into this just at the introductory level in elementary organic, but in Organic 1, this is a big, big topic that you'll spend a lot of time on. We're going to do a lab with modeling. We'll be using the model kits to look at this. And your homework has some stuff with wedges and dashes in it too. Right, so enantiomeric molecules here. If you look at these two, right, there is a mirror. This one is the mirror image of this one, right? This is a mirror image of this. But if you take this molecule and plop it on top of this, does it work? No, that doesn't work. And so anytime you see a little asterisk next to a carbon, that stands for a chiral carbon. It's not something we're going to get into in great detail in elementary, right? It just means that those two molecules are enantiomeric to each other. So here's the same thing just drawn in cartoon form, right? That is the mirror image of that. But if you take this and put it on top, the OHs and the ethyls line up, but these don't. Okay, now this happens in the real world, right? So here are two molecules. You know what spearmint tastes like, right? Mint. And caraway seeds, those are fennel seeds, right? So think about like rye bread. That's what we're talking about there. All right, they have this, these two are enantiomers of each other, right? There's a mirror image, there's a mirror plane right here. But if I take this, I can't put it on top of the other. So those are, and you have, the neat thing about it is you have taste receptors that accept, one accepts the spearmint, one accepts caraway. It's kind of crazy to think about the fact that you can identify those two as a living thing, right? We can actually identify a difference between what the spearmint tastes like and what the caraway seed tastes like. And so this is what I was just talking about. And your brain can actually distinguish between those two. And there's the showing the mirror image, which is what I just said. Your cells are also handed, right? Left-handed versus right-handed. In pharmacology, this is big deal. Maybe one of them, maybe one of the enantiomers is really, really, really bad, and one of the enantiomers is really good, right? If you've got, you know, a Dr. Jekyll, Mr. Hyde kind of thing, got to pull the whole drug off the market. And here's an example of that. Have you ever heard of this? You're taken next door, right? Have we talked about this? So morning sickness was treated with this substance. And one enantiomer was great for morning sickness. The other one caused severe birth defects. Severe birth defects. So you got to pull the whole thing, right? If one enantiomer is great at helping you not throw up, the other one causes severe birth defects, you got to pull the whole thing. Another one is good for treating a disease, the other one has no effect, right? At least if the other one has no effect, that's better than having horrible side effects. Advil, you know, the active ingredient is ibuprofen, has one enantiomer that's active, one that's inactive. So looking at these two, let's decide if they are enantiomers. Is there a mirror image relationship here? Yeah, but if I flip A, if I put A on top of B, will it line up? No, it won't. So that's as far as we're going to get into enantiomers in this class. Basically, we're just going to look at identifying them. We're going to look at talking about them. Any questions before we wrap up today?